All right, good afternoon, everybody. Today we're going to talk about section 2.6, continuity. And this is actually our last section for chapter 2 before we move into something that's a little bit more rigorous and a little bit more calculus-like. So let's get started. So first of all, let's talk about continuity at a point. A function f is said to be continuous at a if the limit as x approaches a of the function f of x is equal to f of a. So let's make this a little bit more succinct with a checklist. So for something to be continuous, one, f of a has to be defined. So we can't have any open holes with no black dots near them. Two, the limit x approaches a of f of x must exist. And three, the limit as x approaches a of f of x must equal f of a. So just because the limit equals the right thing, the limit exists, doesn't mean that it necessarily equals the correct thing. And it should be noticed, I have here in red, that if one item on the checklist fails, then f is said to be discontinuous at a, where a is just some point. So let's go at this with an example. I want you to use the graph of f to identify values of x on the interval 0 to 7, at which f has a discontinuity. Remember, a point is discontinuous if it is not continuous. So here's this graph. Go ahead and pause this video and see if you can come up with places where this graph is discontinuous. And then join me back in a moment or two. So f is discontinuous at x equals 0, 1, 2, 3, and x equals 7. And why is this? Well, at 0, we have an open hole with no definition near it. So f of 0 is not defined at all. We have the same problem with f of 1. And while at f of 2, our limits equal the right thing, we have f of 2 is equal to 3 instead of equal to 1, which is what our limits equal. And we have the exact same problem with f of 3. We have a definition equals 1, but our limits don't equal the same thing, so our limits don't exist. And finally, x of 7. At 7, we have a discontinuity where we have an undefined section of our graph, but the limit only exists from the left. So we don't have a right-hand limit at all. So hopefully that makes sense and we can keep going. Here are some rules about continuity. We assume that a function f and a function g are continuous at a point A. Then the following functions are also continuous. Let c be a constant and n greater than 0 as an integer. So f plus g is continuous if f and g are continuous. F minus g is continuous if f and g are continuous. A constant multiple times a function that's continuous is still continuous. F times g is continuous. F divided by g is continuous provided that g evaluated at a does not equal 0. And a function to some integer power is also continuous. So x is continuous, x squared is continuous, x cubed is continuous. Here's theorem 2.10. A polynomial is continuous for all x. And a rational function, that is one polynomial divided by another, is continuous for all x for which q of x, our denominator, does not equal 0. So let's see some examples. For what values of x is the rational function f of x equals x divided by x squared minus 7x plus 12 continuous? So go ahead and pause this video and see if you can't come up with these values on your own. Welcome back. So because f is a rational function, theorem 2.10 tells us that f will be continuous for all x where x squared minus 7x plus 12, our denominator, does not equal 0. The denominator factors into x minus 3 times x minus 4. So it has zeros at x equals 3 and x equals 4. So our function f will be continuous for all values of x except x equals 3 and x equals 4. So hopefully that makes sense. Now let's talk about composite functions. So given two functions, f and g, the composite function f circ g is defined by f of g of x. So you take x and you plug it into g, you take that answer and you plug it back into f. Now let's talk about continuity of composite functions at a point. If g is continuous at a, and f is continuous at g of a, then the composite function f circ g is continuous at a. So what does this look like? Let's see one more theorem before we get into this. If g is continuous at a and f is continuous at g of a, then the limit of f of g of x as x approaches a is the same as f of the limit as x approaches a of g of x. So what does this look like? Let's do a quick example. Evaluate the following limit, and we're looking for the limit as x approaches -1 of square root of 2x squared minus 1. And I'm not going to make you pause, you can just keep watching. So here our inner function is going to be 2x squared minus 1. 2x squared minus 1 is continuous because it's a polynomial and it's positive at x equals -1. So 2 times minus 1 squared minus 1 equals the value 1. And because the square root function is continuous at 1, we can write the following. Our limit as x approaches -1 of f of g is equal to f, our square root function, of the limit as x approaches -1 of g, which is 2x squared minus 1. That's the same as square root of 1, which is 1. So our answer is 1. Now that we've talked about continuity at a point, it's more important to talk about continuity on an interval. A function f is continuous on an interval I if it is continuous at all points of I. If I contains its endpoints, the function must be continuous from the right or left at the endpoints. And you'll see some pictures in a moment that will explain what I mean by right and left. So here's our first one. This function I'm going to say is continuous on parenthesis a to b parenthesis. So in the case where our interval contains no endpoints, our function needs to only be continuous between a and b. So it doesn't have to be continuous at a and it doesn't have to be continuous at b. It just has to be continuous in between. Now, this is continuous on inclusive a. In the case where our interval contains the left endpoint, our function needs to be continuous between a and b. Oh, thought I had a highlighter. Between a and b, and from the right at a. So that means that when I take a limit from the right, this needs to exist. And it needs to equal f of a. And we see the same thing when we include the left endpoint. In the case where our interval contains the right endpoint, our function needs to only be continuous between a and be continuous from the left at b. So limit x approaches b from the left of f of x must exist and equal f of b. And finally, when we include both our endpoints, our function must be continuous between a and at a from the right and b from the left. So theorem 2.13, continuity of functions with roots. Let n be a positive integer. If n is odd, then f of x to the power 1 over n is continuous at all points at which f is continuous. If n is even, then f of x to the power 1 over n is continuous at all points a at which f is continuous, and f of a is greater than 0. So what does this look like? Let's do a quick example. We're interested in what values of x is g of x equals square root 9 minus x squared continuous. The graph of g, which I have drawn on the left, is the upper half of the circle x squared plus y squared equals 9. And it appears that g is continuous from -3 to 3 inclusive. Obviously the interior is fine, so we need only check the endpoints. Checking -3 from the right and 3 from the left shows us that these endpoints are included. Checking shows us that this is true. So G is continuous on inclusive -3 to 3. And that is when we plug in -3, we get -3 squared, which is 9. 9 minus 9 is 0. Square root of 0 is 0. So our limit approaches 0. And our limit approaches 0 and our function evaluates at 0. And we see the exact same thing with the endpoint to the right. So how would you know this? Well, let's consider plugging in values greater than 3 or less than -3. We're going to get imaginary numbers. And at least in this class, we're not going to deal with imaginary numbers. So if you end up with an imaginary number in your answer, you know you've done something wrong. We're only dealing with real numbers. So we can't have x squared be a value greater than 9. Or we can look at it as g of x equals y equals 9 minus x squared quantity square root. Squaring both sides yields y squared equals 9 minus x squared plus y squared equals 9. And we know that if we put in negative y values, we're not going to be able to put in any x values. Or I should say, there's no x values that we can put in that are going to give us negative y values. All right. So here's another example. For what value of x is f of x equals x squared minus 2x plus 4 quantity to the power 2 over 3 continuous? And for this one, I do want you to take a pause really quick and see if you can't figure this one out on your own. All right, welcome back. So x squared minus 2x plus 4 is continuous for all x because it's a polynomial. So we can rewrite f of x as x squared minus 2x plus 4 squared, quantity to the cubed root. The result of squaring the resultant value of our polynomial will always be positive. And we see that f contains an odd root. Because f will always be positive and continuous, f is continuous for all x. So here are a few slides where all you need to do is know these off the back of your hand. The following functions are continuous at all points in their domain. We have sine, cosine, tangent, cotangent, secant, and cosecant. All of these trigonometric functions are continuous at all points of their domain. Oh no, oh no. What about our inverse trigonometric functions? Well, it turns out that the inverse trig functions are also continuous at all points of their domains. So that's sine inverse, cosine inverse, tan inverse, cotangent inverse, secant inverse, and cosecant inverse. Now, what about exponential and logarithmic functions? The following functions are continuous in all points of their domain. That's b to the x, where b is any value you can think of, any real number. E to the power of x, which is just e to the x. The log base b of x, and remember we usually do log base 10, but we could do log base anything, so log base b of x is continuous at all points in its domain, and the natural log of x is continuous in all points of its domain. And finally, here's the big chunk. This is the big thing. So if you didn't listen to anything else on this lecture, here's the main thing that you need to take home. And this is the intermediate value theorem. I have it in all caps because I forgot to make it not that way. Suppose f, our function, is continuous on the closed interval a to b, and L is a number strictly between f of a and f of b. Then there exists at least one number, c, in open interval a to b, such that f of c equals L. Now, why is it important that we don't include the endpoints? We don't include the endpoints because those need not be defined. And so what does this look like? This looks like if I draw a continuous function from a to b, I'm going to pass through a point c in between a and b, where f of c equals a number between f of a and f of b. And I say there exists at least one number, because there could be multiple values. And we see in the second graph over to the right that if I have a function kind of like sine or cosine that oscillates a bunch, then it's going to pass through that point L multiple times. So the intermediate value theorem is very important and is very powerful, so it's best to remember it. All right, that's it for me.